So today marks the beginning of what we call graph theory. And this is not like what you did in algebra. This is very, very, very different from that kind of stuff. So we're going to start with just the most basic elements of graph theory. Now, with graph theory, what you have are vertices and you have edges. So essentially, you're playing dot to dot like you were when you're little kids. You're connecting dots, and the things that connect the dots are called the edges. So if I have, let's just say I have some vertices. I'll start with something really simple, and I'm going to name them. So V1, V2, V3, V4. These are just four vertices. There's nothing about them that's special. But if I want to connect them, so I'll say my set of vertices. And by the way, all of the graphs we deal with will always be finite, okay? Because we actually will make numerical conclusions in some cases. If I connect these, let's say I decide to connect these two, and I connect these two, and then I connect these two, and I connect these two. And let's call this edge 1, edge 2, edge 3, edge 4. Okay, so I have a set of edges now. Okay, this is just called a simple graph. There's nothing special about this graph. Now, if I decide to put direction in it, graphs do not have to have direction, okay? But if I decide that, you know what, we're gonna think of this as going that way, and that way, and that way, and that way, now I've made my simple graph into what's called a directed graph. Or a digraph. So people see the word digraph and they're not sure exactly what that means, because di is Latin for two. This di is just short for directed. I don't like the term digraph because it's kind of ambiguous. Again, it makes it sound like I have two graphs. A directed graph is one where I basically have arrows. So this would basically be like a traffic flow situation. I have an intersection, I have an intersection. This could represent a one-way street then, okay? So I mentioned this last week. In linear algebra, we do things like traffic flow problems, and we have intersections and how many cars are leading in, how many cars are coming out, and you can control this finite situation, input and output. In this case here, this could easily represent it. Now, what I want to do is I'm going to change this around a little bit, okay? And I'm not worried about the direction. That's just an extra thing. Most of what we do will not be directed. So could I draw a different picture that represents exactly the same thing? In other words, E1 is connecting V1 and V2, and so on. Every one of these edges is very, very specific, okay? What if I did this? I'll put V2 down here. And now I have V1 is still connected to V2. V3 is still connected to V4. V1 is still connected to V4. And these guys here. Now, these graphs cross, but there's no vertex here. That's a vertex, that's a vertex, that's a vertex, that's a vertex. These just cross. Turns out these are identical, and that can be very confusing. And again, there's my E1, there's my E3, 2 to 3 was, there's my E2, and there's my E4. What I did was I just took it and I essentially twisted it. But the same vertices connect with the same edges. So the first thing we want to notice is you can change things. You can represent things differently and it still is considered the same. So there's a term here. We'd say these are topologically equivalent. Now, there's a branch of mathematics, one of the scariest, gnarliest, most abstract branches of mathematics there is, called topology. And in topology, you study things, a lot of geometry, in fact, but at a very abstract level. So if I said, for example, I've got my water bottle. It's closed, it is sealed. There's no holes, there's no openings. We would say this is topologically equivalent to my pen. Meaning, if I thought of this as a lump of clay, I could shape it and mold it and make it look like the pen, and so on. Now, is that the same as, let's say, give me 1 second here. Now, is that the same as this coffee mug? Well, this coffee mug, this handle, there's a hole. Now, you don't say there's a hole on the inside. There isn't, because again, if this was a lump of clay, I could push it and smash it and even make it look like a bowl. Great. I could do all sorts of things. What I can't do is create a hole. Okay. I can't create a hole in something where there's no hole. So this guy, we say, is topologically equivalent to a torus, a donut, because I can bend and shape all this stuff, but I will always have the hole there. So things that are topologically equivalent are things that you could manipulate and bend, but you can't change the basic structure. In other words, V1 was connected to V2 by edge 1. Even though I twisted it and shaped it, V1 is still connected to V2 by E1. If I turned it around, that doesn't change it. It doesn't make it different. So you can manipulate graphs to look like something else. Okay, so I'm giving you a really, really basic example of exactly that. Excuse me. Okay, let me. Now I'm going to define a different type of graph. Okay. This is one of the most common ones we deal with. If I have two vertices connected by one edge, I could have 3 vertices. I could have 4. I'm just going to do this a few times. Okay, but the moment I get to the 4th one, I also want to do that. I want every possible edge I can draw, and I'll do one more with 5. So 1, 2, 3, 4, 5. And I would have that, and I would have that, and I would have that. Each of these has a name. This is called K2, this is K3, this is K4, this is K5. Okay, their K sub n is the name of the graph. And what it is the subscript tells you how many vertices, and then you connect every vertex with an edge. So here, that was pretty simple, but the moment I put a 4th one, there were multiple ways I could connect them. The moment I put a 5th one, I think I left one out here, there's one more there. Every conceivable way I connect them. So that's called Kn, okay? K is actually Kuratowski. You don't need to know that. It's named after somebody who did a lot of work. Now, as the K gets bigger, obviously the graph gets more and more interesting and more complicated. So the first question is, okay, oh, by the way, is there a K1? Anyway, what would a K1 look like?
It would just be a dot.
Perfect. It's kind of redundant, but that would be K1, just one vertex. So the subscript refers to the number of vertices. Edges, you just draw as many edges as you can draw to connect things. Now, is there a way to calculate the number of edges? This is kind of interesting. Well, let's see. Let's write the number of edges in each case. So in this case, there was 0. In this case, there was 1. In this case, there was 3. Now, 1, 2, 3, 4, 5, 6. How about here? This is a little bit harder to see. How many edges do I have here? Well, I have the outer ones. That's 5. And then 1, 2, 3, 4, 5. I think that's 5. So I got 10 there. Oh boy, is there a pattern here? What if I said, K, 12? Well, here's a vertex. And then there's, I'm going to have 12 vertices. How many edges are leaving this guy? Anybody want to guess exactly how many edges should be associated with that vertex? Well,
11.
Good. You notice K3, there were 2 edges. In K4, there were 1, 2, 3 edges. In K5, there was 1, 2, 3, 4 edges. Is there a pattern here? Yeah. every vertex is going to have 11 edges coming out of it. Does that mean the answer is 11 times 12? Not exactly. Not exactly 11 times 12. Why? Because that edge coming out of here is also an edge coming out of here. Okay, so if I go back to here and say, I have 4 vertices and each of them has 3 edges, that's 12, but my answer was only 6. So does it appear that it was 4 times 3 divided by 2? Then how about this one? 5 times 4 divided by 2. So what do you think this one's going to be?
12 times 11 divided by 2.
Ah. Now, how about if I wrote it a different way? How about 12 times 11 divided by 2 factorial? Would that be the same thing?
Yes.
And what would that be?
12 factorial on top.
No, but better than that. That would be...
Oh, a combination.
Does everyone see that? It's a combination. That's more convenient to think of it that way. It's combination 12 choose 10. So therefore, if I said how many edges, okay, so if I have Kn, and n's got to be at least 3, because otherwise I won't be able to have a difference of 2 here. Then the number of edges is going to be n choose n minus 2. How do we know? We just did it. Oh, okay, this was exactly 5 choose 3. This was exactly 4 choose 2. This was exactly 3 choose 1. And technically this was 2 choose 0. That's just boring, right? But I guess really we could say greater than or equal to 2. Oh, how interesting. So you can tell me the number of edges on any one of these graphs. That's kind of nice, because if I have a really large situation. Now, think of this like telephone lines, okay, like in the old days. So you got all your houses on your street and you want to be able to talk to any of your neighbors at any time on the phone. So, you know, if you have telephone poles outside of your house, I have telephone poles outside of my house, and you see all the lines, and from every single house, there is a wire that goes to the telephone pole. Okay, so every house is somehow connected to every other house. But what if we just said, let's make it simple? Like, do you remember when you were kids, you took the tin can and you had the string and you connected it to the other tin can? Maybe you guys didn't do that as kids, but you could talk in one end of the tin can and you could actually hear it in the other. The string carries the vibration of the sound. It's a cool thing that, you know, when you're kids, you do stuff like that. So rather than telephones, we just have, you know, strings going to every house. But this is what it would look like. I've got strings going to every which house. So the question is, how many connections, if you have n houses in your neighborhood, there would be, here we go, n choose n minus 2 possible ways to connect. Now, will they crisscross? Will most of them crisscross somehow or another?
Yes.
Yeah, and that potentially is a problem. And the reason that's potentially a problem, imagine these are, imagine there's electricity involved, or there's, you know, some kind of circuit or something. Hold on a second, I'm gonna stop that phone.
Call from Sharp Health Card.
Yeah, hold on one second. That's actually for me. Hang on one moment here. Not one I could actually miss, unfortunately, in this case. So the question is, if I have the lines crossed, is there a way to know when I can avoid them? So let's do a really simple example of this. Clearly, let's say you got 3 neighbors. You got 3 neighbors, and they could be all on the same row, by the way. Is there a way to connect them without any of the lines physically crossing? Yeah, in fact, I'll even kind of, you know, like that, okay? Have we connected everybody here? Yeah. By the way, edges don't have to be straight. Edges can be curvy. I just did an example of that. Turns out this and this are topologically equivalent. I've still got the same 3 vertices and they're still connected to the same other vertices with the same edges. I just drew it different. So now here's the question. Can you make 4, by the way, you could put them all on a line if you chose. Can I connect these without ever having them crisscross? I want everyone to try that just for a moment. can you connect all the vertices without having any of them cross? That's not as obvious as you think. So I'll do that one, and I'll do that one, and I'll do that one, and I'll do that one. Okay, but I got to get all the other ones. Well, I can certainly do this. How am I going to do these two without it crossing? Anybody want to help me on that one?
Just go from the outside of the bottom left one.
Can I go like this? Yes, I can. And you just did it. You just figured out a way to do all the, if you want to call them telephone lines, without any of them crossing. Beautiful. All right. So let's go to the fifth one. See, when I drew that K4, I had them crossing, but you figured out a way. This is still K4. You figured out a way to draw it without physically having them cross, and I still connected the same ones. So now I wanted to try to do the same thing. Put down 5 vertices and try to connect them without any of them crossing. Yeah, I'll do my part. I'll do the outer ones. Okay. Well, I can certainly go like that. Oops. I can certainly go like that. Now, to connect these two, I'm already connected on the outside. To connect these two, clearly, I would have to go this way. And to connect these two, I'd clearly go that way. Piece of cake. So did we just figure it out? Well, almost. Is there one more set that I haven't connected? Does everyone see it? I've got 4 leaving this one. I've got 4 leaving this one. I've got 4 leaving this one. I only have 3 leaving these two because I haven't connected them yet. Is there any way I can connect these two without them crossing? Anybody?
No.
Now, it turns out you can't. So it turns out from a theoretical standpoint, this is one of the biggest results in graph theory.
The third dimension.
But we're in 2 dimensions. Yeah, that is important to realize. We're kind of stuck in 2 dimensions. You say, well, what if I can go over the top? So every graph has a smaller graph within it. So for example, when I draw, let's go back to this one here. Okay. There is a K3 and a K2 and a K1 inside of this graph. How do I know? Well, just grab any 3 vertices and you've got your K3. That's called a subgraph. Think of it as a subset. So if I have Kn, then Kn plus 1 and Kn minus 1 and Kn minus 2 and so on would all be part of that graph. They'd all be little subsets of that graph. So I just said, well, let's just consider this right here, just that much. The orange, there's K3. So every graph has subgraphs that are part of it. Any graph that has K5 as a subgraph, which means it's bigger than K5, it's not possible to connect the vertices without them crossing. K5 is the first one that it fails for. So anything smaller than K5, like K4, you can. This is considered major theory. This is how in circuitry and electronics and when they're doing telephone poles and stuff. So what did they figure out a long time ago? Well, you have to go underground. See, if all the telephone lines connect, then you have telephone lines that are doing this, and that's bad. You can't have telephone lines crossing and touching. That's bad. That's how you have, accidents and short circuits and things like that. So they figured out a long time ago that they had to go underground and therefore at different levels. So someone said, what about 3D? Yeah, that's kind of what you'd have to do. You have to have different levels so they don't touch. Oh, okay. So if you've ever looked like an old computer and maybe, really, really big computer systems, and you see really gnarly cords in every direction, lots and lots of bunches of cords, and they're just all over the place. Well, you can't have these things crossing, bad things can happen. So this is just sort of an interesting observation, okay? Now, let me give the next type of K graph, and excuse me, it's called a bipartite. Bipartite. Well, bi just means 2. So it's a graph that basically has 2 parts to it, but very specifically, bipartite. Km comma n. So before we did K2, K3, K4, K5. Now I want to do K2 comma 3 or K5 comma 7. So I'll just draw a simple picture. K2, 3 would be 2 vertices, 3 vertices, and every conceivable way of connecting these, but not with each other. So the M on one side connect to the N on the other, and then every conceivable connection. So this would be K2, 3, which again is the same as K3, 2. So it doesn't really matter what order you say it in. So if I said 2, 3, or if I said 3, 2, it's the same thing. I just would orient it. I'd probably put that number on top and that number on the bottom just so I can keep track. So now let's go to this graph right here. Can you draw K2, 3 without any of the vertices crossing? Okay, well, let's do it. I got to get from here to the other guys. Well, okay, that one's easy. Can I go like this? Is that legal?
Yep.
And how about that? Is that legal? We did it. We just drew it without any of them crossing. All right, we're good. We're really good. All right, so we're going to change it now. So it's a game. It's a game that's considered very high-level theory, but it's a game. Let's do K3, 3, and let's do the exact same thing. 1, 2, 3, 1, 2, 3. Now, let's take a moment. Connect these 3 to these 3 without anything crossing. Just take a moment. Let's all try that one. So. See what I did? I gave kind of a little squiggle so you can see where it was going. That's legal. I got it in there. What's the problem though? Can I get those guys? Or is this guy trapped? What do you think?
Trapped.
Yeah. So it turns out for a bipartite graph, K3, 3 is impossible to connect all the vertices without crossing. So any graph that has K3, 3 as a subgraph. So if these guys are 3s or higher, now I'm not saying 4, 2 or 7, 1. No. 3, 3. Both of these guys are 3, 3 or higher, then it would be a subgraph. It's not possible. And again, in theory, those are very, very important things. So I have my neighbors across the street and we want to connect all of our our tin cans and strings. Well, can I do it in such a way that the strings don't cross? That's what I would like to do. Interference, electricity, just there's a plethora of reasons you might want to do that. So it turns out it's an interesting problem. It's not a complicated problem. Now, the question is, how many vertices? Okay, these are pretty ugly graphs. How many vertices is KMN going to have? I'm sorry, not vertices. I'm sorry. How many edges? How many edges is KMN going to have? So let me go back. Let's do a simple picture. Let's go back to the 2, 3, because that might be the easiest one to analyze. So 1, 2, 3, 1, 2, 3. Okay, we just had a chapter where we worked on counting techniques and combinatorics in general. Is this a simple counting problem? Is this a simple matching or multiplication principle problem? Like a dice roll? What do you think? How many edges did we have in this picture?
6.
And could I have
Just 3 times?
This is K2, 3, by the way, unless we forget. Is it simply the product of these two? Yeah, because I'm taking the 2 here and I am matching them with the 3 here. It's the matching that's the key. Remember, we said if I have n1 ways of doing the first thing and n2 ways of doing the second thing, then it's n1 times n2 of doing both of them. There's exactly m times n edges. Exactly, always. That makes it easy. Now, when we did the k sub n, that was different, right? That we're going cross and doing everything under the sun. That had n choose n minus 2. We're a little more complicated. This one's a little more obvious, I think, a little bit simpler, okay? Excuse me. Now, we want to talk about, just go back to now the basic graphs. The Ks are very special. So just a graph in general, what sort of things are allowable, okay? I've got 2 vertices. I can connect them with an edge, call that E1, and I can connect them with a different edge. Whoa. Well, here's your house, here's your friend's house, and all we're saying is there may be more than one path to get there. Oh, okay, that makes sense. I can have more than one way of getting anywhere, potentially, okay? So the question is, let's call this V1 and V2. I want to define degree. Degree is a numerical measurement of something. The degree of a vertex is exactly how many edges are leaving that vertex. So right now, here's the way I like to do it. It's the simplest way to think about it. If I circle V1, I can clearly see there's 2. There's 2 edges leaving it. So the degree of V1, excuse me. Okay. In my picture, what is the degree of V2? Well, would also be 2. So what would the total degree of my graph be? If I added up the degrees of each vertex, what would the total degree of this graph be?
4.
4. But I only have 2 edges. I have 2 edges, but the total degree is 4. Just so we kind of on the right track. Let me put another one out here. So now I've got that guy right there. Okay, I'm just going to throw another vertex out there. So now I have, squeeze it in here. Now we'll say we have the degree of V3 as well. Well, did anything change? The degree of V1 is not 2 anymore. Now what's the degree of V1? 1, 2, 3. Degree of V2 is still 2. What's the degree of V3 in my picture?
1.
1. So what's my total degree now?
6.
6. How many edges do I have?
3.
3. Anybody notice anything? This may be the single most important of all the results.
Oh, it's 2 times?
The degree of a graph is always twice the number of edges. And the reason's really simple. An edge has a starting and an ending. So each of those vertices gets a count. Okay. This is not that dissimilar. If I'm a big football fan, okay? And so when you're looking at the schedule, in NFL, there's 32 teams, and before this season, everybody played 16 games. So you have 32 teams, 16 games. That's 512 games. But are there really 512 games? No, there's only 256 games. Why? Because a game always involves 2 teams. So each team that played in the one game gets to count that as a game. Every edge connects 2 vertices, so each vertex gets to count that edge as part of its degree. It's actually the exact same mathematics. The number, so if you're looking at contests between anybody, tennis matches, football games, hockey games, they're involved 2 players or 2 teams. There's one game, but involves 2 teams. So each of those players or each of those teams gets to count that in their overall count of games played, which would be the equivalent of degree of the vertex. So then what if I did something like this? I'm going to put another edge here. There's another edge. So we called that one edge 3. I'm going to call this one edge 4. But edge 4 just, I left my driveway, did a little circle, and came back to my house. That's okay. This is called a loop. A loop is still an edge, but it's an edge connecting the same vertex to itself. Okay? A loop is absolutely legal. There's nothing wrong with the loop. They can go anywhere. I live on an island. Can't get to somebody else's house. Now that changed something. That changed something hugely. What is the degree of V3 now? Is it 2?
3.
Remember what I said about draw a little circle? If I draw a little circle around the vertex, I got 1, I got 2, I got 3. The fact that it's the same edge, I'm leaving in this direction, I see it, and I'm leaving in that direction, and I'm leaving in that direction. So the degree of V3 right now is 3. Okay, and again, my total degree now is 8, which is 1, 2, 3, 4. The loop counts as one edge, but because there's 2 different routes I could leave the vertex, I get 2 in the degree count for that vertex. So loops are very important from that, in maintaining the count. So the total degree of a graph is just the sum of all the individual degrees. That's easy. That absolutely must be twice the number of edges. Therefore, somebody tell me something about the degree of any graph, every graph that exists, all infinitely many. Tell me something about the degree.
Always be 2 times the vertex.
Therefore, it's always going to be
more than.
If it's 2 times something, it's always going
double.
to be. It's always going to be, starts with an E.
Even?
Ends with a Ven. Yeah. It's always even. The degree of a graph has to be even. It would be impossible for it to be anything else. Now, what would be the most boring graph? There's my graph. Just the dot. What's the degree of this vertex? There's no edges. So what's the degree?
0.
0. Now, I'm not going to put any more vertices. I'm not going to put any more vertices. I'm going to give you a loop. In fact, I'm going to give you 3 loops. There. I just created 3 edges. Now, what's the degree of V1? 1, 2, 3, 4, 5, 6. There's 6 different paths. I created 3 edges, all of them loops. The degree of V1 is now 6. The degree must be even. And by the way, I can have 0. There's nothing wrong with 0. All right. 0 is totally legal. It's not that it's not exciting or anything. So, excuse me. If I drew a simple picture, and by the way, you notice these pictures, I'm not putting directions. I'm not giving you arrows because it's not important. That doesn't change things like degrees. So if I'm going to do a simple picture, and I'll label everything. And let's see. Let's call that V1, V2, V3. And how about, let's call that one E1, E2, E3, E4. So I'd like the degree of V1, the degree of V2. This is a simple exercise, the degree of V3. And as a result, the total. Anybody want to help me out here? So what's the degree of V1 in my picture?
6.
V1.
3.
Just 3, yeah. Okay, how about the degree of V2?
3.
3. And the degree of V3?
2.
And so therefore the total degree would be, we agree 8. How many edges were there? I mean, I could label them, that makes it easier. 4 edges, total degree of 8. That makes perfect sense. That's what we just said a moment ago. Okay, so let me make it a little more complicated now, because we want to make sure we're interpreting this correctly, because this is not difficult. We're going to use this to answer bigger questions. So let's do one. And let's see, I want to go that one, and I want to go that one. And let me call these guys. Let's say I've got V1, V2, V3, V4, and we'll call that edge 1, edge 2, edge 3, edge 4, edge 5, edge 6, edge, I think that would work. Let's see. Okay. So for this graph, actually, I'll just do it up here. I've got 4 vertices. All right, so let's holler it out. What's the degree of V1?
4.
4, good. Because I can see 1, 2, 3, 4. Even though there's only 3 edges, there's still a degree 4. How about the degree of V2?
5.
5. I want that to be absolutely obvious. V3?
2.
And V4?
3.
Is it possible? Is it humanly possible that I miscounted on any of these? Obviously, the
Possible.
answer is yes. My total degree is 14. Does that fill me with confidence?
Except
I have exactly 7 edges. My total degree was 14. Unlikely I made an error because I would have had to make multiple errors. I can't get the total degree to be exactly double the number of edges if I have errors along the way. So I'm pretty confident I did it right for exactly that reason. Okay. Any questions so far? So now we want to do an exercise. This is where you get to be a bit creative. I want you to draw a graph. We'll keep it simple with 3 vertices of degrees. Let's say 1, 3, 4. So everyone to try this on your own just for a moment, and we'll just sort of compare answers. Okay, so everybody on your own, draw a graph with has 3 vertices. And by the way, your vertices can be on a line. You can make it triangular, do it however you want. Doesn't change anything. So I need the degrees to be 1, 3, and 4. First of all, is this even possible?
yes.
Yes, because what? You're right, but why are you right?
Number of edges, number of vertices is twice, no, vice versa.
Well, because the total degree would be 8. So what does that tell you in your construction of the graph? You have 3 vertices. Exactly how many edges you're going to draw?
4.
4. That's the key. That's why I said, is it possible? Because that sum is even. Yes, it is possible. Now I'm gonna draw it in a triangular orientation. All right. Let's call that V1, V2, V3. All right, there we go. Now, if V1 is my vertex of degree 1, can I have any more edges leaving V1 then?
Nope, that's it.
No, that's it. Yeah, it's kind of boring. So,
And a couple of loops, maybe.
You connect V2 to V3 twice.
oh, I could do that. Okay, wait. Okay, hold on, because I heard an alternate. That's very important. All right, so let's do, the first comment I heard was, let's connect these guys twice. That's a terrible picture, I know. I'm connecting these guys twice. All right, are we there yet? Are we there yet?
You just got to do a loop for V3.
Okay, I can do a loop for V3. Does this work?
Yep.
Okay, now give me an alternate approach. I heard someone said a couple of loops.
Yeah, I did it. I don't see the board right now, but
will that work?
Yes,
Yep.
That's what I did.
1, 1, 2, 3, 4, 1, 2, 3. Are these the same graph? Are these graphs topologically equivalent. Another term we could actually say is isomorphic. If you had linear algebra, you're familiar with that. Are these graphs isomorphic?
Yes.
You sure? This has two loops. This has one. Oh, this has a repeated edge. This doesn't. No, actually, they're completely different graphs. They both satisfy this, but we came up with two completely different graphs. Isomorphic would be this. Let me redo this one linearly. These are the same.
Gotcha. Okay.
Does that make sense? All I did was swing it wide.
Yeah.
Now, if I do this one, maybe it'll be easier if I do it from this orientation. I've got a loop and a loop. Say, oh yeah, clearly they're not the same. I don't have any loops here. I have a loop here. These would be isomorphic, or in this topologically equivalent. But both of these are saying the same thing. So kind of a cool little exercise. And the nice thing is there can be more than one right answer. So the quiz associated with this is pretty simple if you pay attention to the detail, but we're just learning. So there are some questions that will come up. Let me grab my textbook. I don't know which book you guys are all using. Okay, so I'm going to refer to something in this book. Oops, hold on. In your textbook, if you have the 4th edition, it's in a different place. That's all I'm saying. In this textbook here, let me find it. There is a very classic problem. If I can actually find it, I might be in the wrong section. Oh, here we go. I'm going to hold this up so you can see it. Find this picture in your book. If you're using the 4th edition, it would be section 10.2. In the 5th, it's 10.1 on page 678. It's a picture of a city called Kronosberg. And there's a very, very, very famous problem. It's in Germany. There were 7 bridges in this city. Okay, because there was different waterways, and there's 7 bridges connecting the different land masses. I think the closest thing to that would be Portland. You ever been there? A lot of bridges, a lot of waterways. So the classic question was, is it possible to pass, to cross all 7 bridges without ever crossing the same bridge twice? So could I get from point A to point B? And can I get to every one of them? Yeah, I can get to every single one of these land masses. But can you do it without ever crossing a bridge twice? This is a very, very classic problem in what we're dealing with. We will discuss this problem next day because it's actually the next section. But there's a mathematical interpretation that says, based on the vertices and the edges that I'm aware of, yes, it can be done, or no, it cannot be done, because it has a lot to do with degrees and different things like that. But it's again, a very, very cool problem. Can I do it? Can I not do it? Because if I'm doing certain things, so we're going to be talking next day about what happens if I've got a bunch of vertices and a bunch of edges. Can I get from any one place to any other place? Can I automatically do that? And also, can I get there without ever retracing my steps? Or is there a way, maybe, for example, you like to hike and you get to certain junctions and, the trail, you have 2 or 3 different options. Can you walk every aspect of the trail without, again, ever retracing your steps, or maybe without ever coming to the same junction? This is not an obvious question. This is something we're going to explore and look at next day. So I'm going to stop here.